Well, hi everybody. Good morning. There's some construction going on across the way here from my parents' house, so you might hear some pounding from time to time. So we're going to start with making sure that we know how to draw structures quickly from formulas, but also knowing how to be able to show their lone pairs of electrons. So what we have here, and what you're going to see a lot in organic molecules, is you're going to see a chemical formula oftentimes written as a condensed chemical formula. It'll oftentimes look like this, and it is in the order of the way you see it written in its Lewis structure. So this CH3 part is right here, the NH part is right here, and the CH part is right here. Now, that's all cool and everything, but we also have to be able to show lone pairs so that we don't lose points on lone pairs. And so one thing we're going to want to make sure is that everything has a complete octet based on how it is drawn. So we could take a look at the carbon, and it has 4 bonded pairs around it, so that's 8. Each hydrogen has 2 bonded pairs next to it, so that's 2. But the nitrogen here is somewhat of a problem. It only has 6 bonded pairs of electrons around it, so we can infer, and this is going to be nothing more than an inference, that that nitrogen is really supposed to have a lone pair of electrons there. We can repeat the same process with each of these molecules, and we see this one is the CH3, and then we have a CO followed by a CH3. And for this to work like this, this has to be shown, or it has to have its complete octets. So the first carbon number 1, has 4 bonded pairs around it, so yay. That's complete octet. And then carbon number 2 actually does have 4 pairs around it because it has 2 here, 2 here, 2 here, and 2 here. So the only bonded pairs or unbonded pairs of electrons that are needing still to be shown are those around the oxygen. So those should be right there. And then, of course, that last carbon number 3, has a full octet around it as well. And once you get the hang of this, you will quickly start to see where you are actually getting used to, oh, okay, well, I can see that this oxygen is going to need 2 electrons, and that carbon is full, but this nitrogen needs 2 electrons here. And so we end up with being able to complete the octets using all of the rest of the valence electrons, which you've already practiced doing in your Lewis structures, but you might not have realized we're actually missing from these compounds. So that's what you see. Right down here at the bottom is C double bond to O, and there's 2 electrons here on this O and 2 electrons here on this O. And so we have to be able to write out, these are called full structural formula, full structural. These ones with all of the bonds showing. These that where they're all written together with no bond showing are called condensed structural formulas. And then we can have a partial condensed, partial full, and I'll show you what all that means. So let's take a look at that part of our notes so that we can make that work for us. Okay, so types of formulas we have are full structural, and full structural shows all the bonds, all the elements, and of course all the lone pairs. Okay, we can also have a partial structural, which shows only bonds between carbons. Otherwise, it would show us the major things attached to those carbons. So in this case, with this is a full structural right here. To get a partial structural, let's just say partial structural, we would end up with CF3, and then we'd have a bond, and then we'd have CH, and then we'd have a bond and OH, just like that. What about if we had a condensed formula? A condensed formula is when you are basically just show none of the bonds and shows only the order of bonding. So the order of bonding in this case here would be it gets written as CF3CHOH, and that is a condensed structural formula just like this, with of course this being our partial structural formula. The very last type of chemical formula we have are molecular formulas. The molecular formula does not show does not give any hints as to the Lewis structure. Instead, a molecular formula for this would say I have 2 carbons, I have 1, 2, 3 hydrogens, I have 1, 2, 3 fluorines, and I have 1 oxygen. And so that would be my molecular formula, simply telling me what and oftentimes the molecular formula is the empirical formula if it is in its lowest whole number ratio. So that is the difference between our formulas. Okay, so let's go ahead and practice drawing those above molecules as condensed structural formulas so we get the hang of it. So we already did the first couple, but we'll go ahead and draw them out as condensed again. So this one, if it is condensed, we have a CH3. From left to right, we're going to write it down, NH, followed by a CH3, and that is going to be our condensed structural formula. All right, so we can repeat the same process for each of these molecules. And so we have here the CH3, followed by the CO, and then the CH3. On this one, it's a little bit longer. We have a CH3, followed by a CO and an NH, and then a CH2, and lastly ending up with a CH3. On this one, we have a CF3, then a CH2, and then what we have is an OH at the end there. On this one, it looks a little bit complicated, but it's going to be okay. We have a CH3, followed by a CH, and then we have a C, which has 2 CH3s attached to it. So we are going to be able to place those into a parentheses and put a 2 on the outside of it. Now, when you're looking at a condensed molecule like this, you might be going, okay, well, how will I know how it's formed? Because I can see right here that this one has a double bond, and I want to point this out to you. This double bond ended up being right here in between this point here. Now, I want you to keep in mind that this carbon has a complete octet because it has a single bond with 2 electrons, another 2 electrons here, and the total of 4 in the double bond. And it appears that this one does not have a complete octet. If you just didn't know there was a double bond there, you might think that both this carbon here and this carbon here both did not have a complete octet. And then when you start to draw it, you realize you are going to have to draw in that double bond there to complete their octet. So this type of area that you see in a condensed formula might give you a hint that there is some kind of multiple bond going on. And you'll notice the same thing happen again. Instead of starting at the end with a CH3, we're starting with a CH2. Automatic red flag, you're going, oh, there's going to be a double bond of some kind, or maybe a triple bond, but it's followed by a CH. Another hint, we don't quite look like we have enough hydrogens to complete octets, so we must be having a multiple bond. Then we have a CO, and lastly, we end up with a CH3, and as you can see, CH3s always just have single bonds. All right, so let's go ahead and move these things forward then. So what if we have to go backwards? That's exactly what we were just referring to. What if we have to go backwards? We want to be able to show our lone pairs. We want to be able to show our format. So let's just go ahead and move backwards. And this is how it's written. So I know the order in which I'm going to draw out my Lewis structure. I have a C with 3 H's attached to it. And that is followed by connected to another C, but this C only has 1 O attached to it, followed by another C. And oftentimes you might wonder, well, is that O going to be in the chain? So I'm going to draw it out as if it were in the chain. And there's that. And then, whoops, that's not a C, that's an N. I end up with N with 2 hydrogens attached to it. So I have this going on. And the only way for me to check if this is going to be the correct way or if this. Let me go ahead and draw out all my hydrogens again. Okay, so one of the things I know right away about nitrogens is they almost always bond where there's going to be a lone pair of electrons right here. Now, the only way you're going to be able to tell till you get used to naming and what functional groups look like is you're going to have to count valence electrons. So let's count up our valence electrons. I've got 4 for the carbon, plus 3, 1 for each hydrogen, plus 4 more for the carbon, plus 6 for the oxygen, plus 4 more for the next carbon, plus 2, 1 for each hydrogen, plus 5 for the nitrogen, plus 2 more hydrogens, so 2 total electrons. When I add that up, let me quickly do the math. 4 plus 3 is 7, plus 4 is 11, 17, 21, 23, 28, 30 electrons. I have to show 30 electrons total. And if I go count this up, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I got a problem. I got lots of problems. I've got 24 electrons, and if I go putting in all my lone pairs that I'm missing, I would have 26, 28, 30, 32. That's not going to work because I'm only allowed to have 30 electrons. So this one is automatically going to go away. Now, what about if I have it this way? Now, if I have it this way, I have a total of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so 24 electrons used, and I have a total of 6 more electrons I can show. I've already shown these here, so I can put 1, 2, 3, 4, 5, 6. Now you might be going, hey, that's cool, that's it. Except that while the carbon has a complete octet, the oxygen does not have a complete octet. So remember what we have to do when the oxygen does not have a complete octet, or when anything does not have a complete octet, we're going to have to move electrons. So I'm going to move those 2 electrons into this double bond, and that's where I get my correct structural formula. Okay, so let's try another one. Another one, I'm going to go in order from left to right. CH3, so there's my CH3. It's going to be bonded to a carbon, and it's going to be bonded to 2 oxygens. And I'm going to go ahead and make an assumption that one's going to go there and one's going to go there. It rarely, if never, has both oxygens in the carbon chain. Usually when you see 2 oxygens together like that, one is hanging outside the carbon chain and one is within the carbon chain. So next comes my next carbon, and it's got 1 hydrogen on it. And my next carbon, it also has 1 hydrogen on it. And then I'm ending with a CH3, which, as you can see, anytime you have a CH3, those octets are completed. But you might notice right away that this carbon and this carbon both do not have a complete octet, so probably there is a pair of electrons here that is going to need to make a double bond there. So we're going to guess, because of the way it's written, that that's going to be a double bond there. Okay, so then I end up with some oxygens, and I have to figure out what is going on here. Oftentimes, we're going to need to use those valence electrons again. So I've got 4 plus 3 is 7, plus 4 is 11, plus 6 plus 6, so 11 plus 12 is 23, plus 4 more is 27, 28, 32, 33, we're up to 30, 33 plus 4 is 37, plus 3 more. So this time we have 40 electrons we need to show. What I was just doing was counting up my valence electrons. So right now I have shown 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. I have 10 more electrons I need to show. So 10 more electrons means I can go ahead and put 2 here, and then 2 more here. And then I can go ahead and put 2 more here. So I've used 6, and I've used 8, and I can put those 2 down there. And if I do that, I see right away that, in fact, that is not going to work because my oxygen will not have a complete octet, so I'm going to need to double bond right there. So you see how we're having to use the valence electrons. Will I always have to use valence electrons? No, you're going to get very, very used to what the functional groups look like and how it should all be written. But this is the beginning stages and you don't know those things yet. So let's go ahead and go on to the next one on our list here. Okay, the next one looks really, really long. And so we're going to go ahead and draw it all out just like you see. I have a CH3 first. And then I have a CH. And then it says OH. Do you guys all see that OH? When you see an OH together like that, that means that it's a separate thing with an O and an H dangling off your carbon. It is then followed by a CH2. So there's my two H's. And then I have a CO and then followed by an NH. Okay, so this is another one. And this thing here, this grouping here, oftentimes you're going to need to get used to, is going to result in a double bonded oxygen there, followed by a nitrogen here, which has a hydrogen bonded here, but that nitrogen is bonded to, as you can see, another CH2, and then a CH3. And we can go ahead and assume there to be 2 electrons here, and total of 4 extra electrons on that one, and then we end up with 4 extra electrons here. Now you might be wondering, why are we drawing in the lone pairs? It's because you need to be able to say what hybridization things are. It's because you need to be able to say what electrical geometry things have. So for instance, if we were to be asked, what is the electrical geometry of the oxygens in this molecule? So remember, electrical geometry takes into account not only bonded pairs of electrons, but also lone pairs of electrons. Okay, so in the case of oxygen number 1, and we're going to call this oxygen number 1, and we're going to call this one oxygen number 2. Oxygen number 1 has a total of 2 bonded pairs of electrons and a total of 2 lone pairs of electrons. And when it has 4 things, bonded pairs and lone pairs around it, we can say the oxygen number 1 is going to be tetrahedral. But let's look at oxygen number 2. Oxygen number 2 has a total of 1 area of bonding. Notice my terminology just changed. It's because the electrons are all located in one spot. So 1 area of bonding, and then it has 2 lone pairs, and this leads us to the trigonal planar sort of format. All right, and so that's why you're going to need to know where the lone pairs of electrons are. Then you would be able to say, well, this one is sp3, while this one is sp2, if you are asked hybridization, and IB will ask you that. Okay, we're going to move this along here. Okay, another way to show a organic molecule is to show it in a line drawing. Each of the lines now are just representing the bonds. So you can see where bonds are occurring. You can see where double bonds are. And what you need to know is that each and every juncture is where there's going to be a carbon. All right, so that means right here, this juncture has a carbon, as does this one, as does this one, and this one. This one here, this one here, this one here. So you're seeing me fill in carbons everywhere. There's carbons, 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 carbons. And you're going, oh my gosh, there are so many carbons. There's never going to be not carbons. You're right. You're in organic chemistry and there's always going to be carbons. Now you'll notice right away that none of these carbons written this way have a complete octet. Holy crap. Why don't they have a complete octet? Well, they don't have a complete octet because you have not shown the hydrogens. So each time you have a carbon at the end of a bond, you can assume that there are also 3 hydrogens around it to complete its octet. So all my carbons at the ends of their bonds down here, and this one here, and this one here, all have 3 hydrogens to complete the bond, as does this one here. Now, the rest of them, we are going to have to be careful about counting the number of hydrogens they need. This carbon is bonded to 2 other carbons, so that means this carbon has to have 2 hydrogens. I'm trying to decide where to put it. 2 hydrogens attached there. This carbon, however, is bonded to 1, 2, 3, 4 places, so that carbon remains alone. This carbon is bonded to two other carbons, so it's got two hydrogens, as does this one. But these two carbons right here, and I'm going to change their color, these two carbons right here, this one here and this one here, both will remain without hydrogens because they already have full octets. That is not the case of these other carbons. This carbon here is bonded in one case here and a double bond here, so this has a CH, as does this one. And this one is 1, 2, 3, 4, so this one just remains a C. This one has 1, 2, 3, so that's going to have an H here. This one will also just have one H because of the three other things or bonds around it, as does this one. This one remains all by itself because it has four things bonded around it. This one gets its H. This one does not have anything but two things bonded around it, so it will be expected to have two other H's. So if you had to, from a lone pair of, from a linear drawing like this, if you had to, you could construct it into a partial full structural like this. This is a partial full structural, or you could draw it out as into a full structural like you're seeing up here. And so that's where we got this and this are the same thing. And so that is a linear drawing. So you might be wondering, well, what is it showing me? Well, let's take a look here. What if you have this? This is your compound. Well, I want to know what is its condensed formula, and I want to know what its molecular formula is. So that means I'm going to count carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. That means I have 6 carbons, and I'm noticing that it's all single bonds. So you might remember from last year we talked, or maybe previous year, we talked about alkanes, and alkanes follow a format of CnH2n plus 2 to determine the number of hydrogens. You could go count them all, but you could always just use this equation. Alkanes mean all single bonds. So I could figure out the number of hydrogens by doing 2 times 6 plus 2. So this comes out to 14. Now let's make sure that we understand that. Here is a carbon, and it's at the end, so that's going to give me 3 hydrogens. Here is a carbon, and it's in the middle, so it's going to have only 2 hydrogens. This one too will have 2 hydrogens. This one too, also 2. This one too. But this is a carbon at the end, and it's going to have 3 hydrogens. Now count them up. Oops, I needed my 2 here. 5, 7, and 5, 7. So we end up with 14 hydrogens. Okay, so you're going to see line drawings like this. And why do we have them? We have them because it's much easier to draw this out to represent the hexane molecule than to, this is called hexane, than to try to draw out all the things, because as you can tell already, it gets very tedious very quickly. Okay. Okay, I want to find one that I like better. I don't like these molecules because they get unnecessarily, what I want to, let's just do one, and I want the molecular formula. What is the molecular formula? Okay, so I have to be able to identify where all my carbons are. And there's a carbon, and there's a carbon, and there's a carbon, and there's another one, and there's one. Okay, and then I have to be able to identify where all my hydrogens are. So I'm expecting another hydrogen here. I'm expecting 2 hydrogens here. I would expect 1 hydrogen here. 1, 2, 3, 4, no hydrogens there. 1, 2, 3, 4, no hydrogens there. 1, 2, 3, 4, no hydrogens there. So for my molecular formula, I would count up my number of carbons, hydrogens, and oxygens. So let's count carbons first. 1, 2, 3, 4, 5, 6. C6. Hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. H8. And oxygens. 1, 2, 3, 4, 5, 6. And there we go. That is our chemical formula, molecular formula that goes with it. How would you know from that how it's all bonded together? You would have to be told the name, or you would have to be told some more information to know what kind of molecule you have, like, for instance, how does it react and so forth. Okay, that's going to come later on, so we're not going to spend our time worrying about that right now. All right. Okay, so we're going to go ahead and stop ourselves right there and give you some practice time to be able to try these out on your own. Thank you, everybody.